What's up, Michael?
Hello.
Hi.
Hello.
Just wait for people to join. How's everyone doing today? All right. Any questions before we get started?
Not for me.
Okay. All right. So on to the next topic. We've now built a Lebesgue integral, and we can start. We've started studying the space L1. And now we're gonna study some more refined properties, or try and go back to the questions that we posed at the beginning of the section on measure theory, and see where we can get. So I'm gonna this is based on chapter 3 in the Stein-Shikharty book, but we're gonna focus on one of the problems there. So the question we're going to ask is about the fundamental theorem of calculus and the conditions under which the fundamental theorem holds. So there are two sides to kind of sum up the fundamental theorem of calculus. So problem one. So suppose we have f that's an L1 function, it's an integrable function on a closed and bounded interval AB. And let's let f be its indefinite interval. I.e. f of x is the integral from on the subset of AB, the integral from a to x of f of y dy. This is definition of f. If f is integrable, the question that we want to ask is, if f is integrable, is the function capital F differentiable? And does its derivative just equal little f? Is f differentiable? At least almost everywhere. And does f prime of x equal f of x for almost every x? So this is problem one. So note that it would generalize the fundamental theorem of calculus, where typically in an analysis class we assume that that little f is a continuous function, right? In which case the fundamental theorem of calculus holds, and the answer to this question is yes, in the case that little f is continuous. Problem two, which we're I think we're not gonna study in lecture because it's not too related to the rest of the class. Um, but it is important. Analogous is important in analysis is the the converse statement to the fundamental theorem. So on under what conditions on F um, do we have that F prime exists almost everywhere. F prime uh, integrable, and f of b minus f of a is integral from a to b of f prime of x dx. So this is the converse, the second statement of the fundamental theorem of calculus. So we're going to focus on problem one, because it turns out that the techniques to solve this problem are have wide application. In fact, problem two is the book nicely explains this problem is called the class of functions of bounded variation, and gets into a bit the question of rectifiability of curves. So it's an interesting subject in its own right. And I'll encourage you to read in the book the material related to problem two. But for the purposes of our class, we're going to solve problem one. It turns out that these techniques are critically important to Fourier analysis. Okay, so let's attack problem one. So okay, so how do we do this? So if we let f of x, remember we're going to try and find so f is in L1 of, say, the interval AB. Capital F is the integral from a to x of f of y dy. And the goal is to study the differentiability properties of capital F. So to do that, we start by studying the difference quotients. So so study f of x plus h minus f of x divided by h as h goes to 0. All right, but this is just, but then this is, we can express this in terms of the integral. This is 1 over h times the integral from x to x plus h of f of y dy. And we're going to generalize the higher dimension. So I'm going to write this in a funny way. So so let capital I sub h be the interval x to x plus h. So we're going to study it for a fixed x, study these intervals I sub h around x. And then the above, this is just equal to 1 over the length of this interval I times the integral over I of f of y dy. Right? And so the question is, for which x do we have the limit as I goes to 0 okay, so this is a reframing of the question. I just changed the notation slightly. It didn't do anything, right? But note that this is equal to this quantity here. This is an average of f over I. Right, we're just integrating the function and dividing by the length of the interval. So this is like computing some type of average of f. And then the claim is that, well, if the function's nice enough, for example, if the function's continuous, we know, right, from the fundamental theorem of calculus, that as we just shrink the length of this interval I, we recover f again. Okay, so the techniques that we'll use to study this, or the big tool is called the Hardy-Loewen maximal function, and there's no it turns out that this is one of these a type of problem that's easy to generalize to higher dimensions, and it just makes sense to do it all at once. So the reframing of the question, in RD, actually maybe I'll put this on the next page. So just take f to be an L1 of RD. And the question, do we have the limit as the measure of the ball, maybe tends to 0, x is for almost every x. So this is the analog of this question in higher dimensions. So instead of integrating over an interval I, we're just going to integrate over all balls that contain x, the point x. So we're going to fix an x, integrate over any, and then take an average of f over any ball that contains x. So the balls don't have to be centered at x; it's just any arbitrary ball, and we're going to try and take a limit as the measure of the balls go to 0. Okay, so this is our question, and so the remark, as I've said out loud already, this is true for every x if f is continuous. If f is a continuous function. Why? So if f is continuous at x, or rather, maybe I should just say it like this. True, maybe I should say a weaker version of this. True if f is continuous at x. Let's just make it a local statement. Why? If f is continuous at x, then for every epsilon bigger than 0, there exists a delta bigger than 0, such that if x and y are within delta of each other, this implies that f of x minus f of y are within epsilon of each other. And then just take if B is a ball that contains X and the measure of B is less than delta, then integral 1 over the measure of the ball of this ball of measure less than delta, radius delta, integral over ball of f of y dy minus f of x. This is just equal to dy, right? Because for this latter term here, I just rewrote f of x as f of x times 1, where 1 is equal to the integral of the integrator function over the ball times the 1 over the measure of the ball, right? So I can pull f inside the integral like this, and then this is just less than or equal to then this equal to this, which is less than or equal to epsilon. And x is in B. Right. So at points of continuity, this is clear, and so the meat of this theory is going to be we're just going to consider an integrable function f, right, which can be a nasty function. Remember, it can be nowhere continuous, right? And it is a question in the chat: do the balls have to be closed? No, no. Yeah. So that won't make a difference in this theory. So as we okay, so which balls are you're asking, like, which balls are we considering? We can pick, I guess, how we ask this question, right? I guess if we're just interested in this first question up here, then it makes sense. Then we would be considering like the closed balls. But right, the measure of the boundary is negligible, right? So we'll get the same result whether we consider open or closed balls. So we don't need to require the openness to be open or closed. You can consider either class of balls. You could also ask, okay, what other types of sets can we consider taking averages over, not just balls? We do rectangles, squares, things like that, or different types of sets. Points containing sets that contain x, and that's a little bit delicate because you get some funny things if you let the set become, like, if you take rectangles, for example, and let the rectangle be like say a fixed width one, but then have height shrinking down, you can get some funny things happen there. So there is some delicacy. There is a little bit of delicacy in this type of averaging question about what types of sets you allow in this limit. But for now, let's just stick to balls as a first pass. Does that make sense? Does that answer your question, Andy? Good. Okay. All right. So rather than study this directly, try to understand such a limit directly, we're going to study a different object, namely, we're going to let me write this down. So rather than so first we're going to replace f with absolute f, and then we're going to replace this limit with a soup, and we're going to define what's called the Hardy-Lilliard maximal function. So definition. So we're going to study a slightly different but related object, and try and understand this fully. And this is the object that turns up everywhere somehow in analysis, harmonic analysis, Fourier analysis, etc. So the Hardy-Lilliard maximal function. The definition, so for f in L1 of Rd, define f star of x to be equal to the soup. So the x dependency is going to come in and where we take the soup over. The soup over all balls that contain x, 1 over the measure of a ball in this soup, integral over the ball f of absolute f of y dy. Okay, so this is the maximal function. Other notation commonly used, you might guess like a mf of x for maximal function of f. Okay, and as in speaking to the life of leisure that mathematicians lead, apparently this came up when and this is according to the anecdotes in your book, when Hardy and Littlewood were talking about cricket. So they were the game of cricket. So this discussing cricket, they devised this maximal function to study some type of averaging problem, and it turns out they struck gold. Okay, so the theorem that will prove. So one immediate one to ask is, what type of function is this? It looks just at some funny things are happening. We're computing an integral of absolute f over a ball, taking some type of average of its absolute value, but then we're taking this soup. So just at first glance, it's not immediately clear that this is a nice object at all. But we have the following theorem, important theorem. If f is an L1 of Rd, then one, its maximal function is measurable. Two, it's finite almost everywhere. It's not necessarily finite everywhere, even if f is. It's finite almost everywhere. And three, f star satisfies the following bound. Estimate the measure of the set of all x in Rd such that f star of x is bigger than alpha. So the measure of the set is less than or equal to some absolute constant a divided by alpha, which appears on the left-hand side, times the L1 norm of f. Okay. So this is called, let's call this, rather this whole inequality. This is called a weak L1 bound, or weak type L1 bound. Or weak type. And so it's in particular, this is a weaker estimate than, so what we would like to say, the estimate that you might try to shoot for is that you can control the L1 norm of f star of the maximal function of f by the L1, by some constant, possibly big constant, times the L1 norm of f. So that would be an L1. That's what's an L1 estimate. We can't prove such a thing. That estimate's not true. In fact, there's no such constant. But we can prove this, which is it turns out that estimates like this are suitable replacements for an L1 bound. So right, this maximal function is an operator. So m. So this is why this is funny notation from the book. Sorry, so we have an operator m, where it takes f and spits out f star, right? So it takes a measurable function and turns out by this theorem to a measurable function. And you can ask, is M bounded in L1? So I can ask, this is just a aside, about mapping properties of M. I can ask about mapping properties of M. In particular, do we have M takes L1 to L1 in a bounded way? And the answer is no to this. Rather, you just have we just have the weak estimate, have the weaker estimate.
I have a question about the statement here.
You have a question? Sorry, I didn't hear the last part.
I have a question about the statement of, I think, 3,
yes.
The estimate. So what is this constant A? Is it independent of F?
Sorry, yeah. So A, that's important. So A is a universal constant independent of F and alpha.
Okay.
Okay, so A is just going to be some number that we can we'll come up in the proof. The number, I guess A. I think A is a function of just the dimension. So it'll depend just on the dimension D, but not on the other objects of interest in particular. So there's no, typically when you write an inequality like this, so A depending on F would be quite bad, or the inequality would have very little meaning, or if it depended on alpha, or if A, there's also some alpha dependence on A. So what's crucial here is that I just have alpha here. I've told you what the alpha dependence is. I tell you what the F dependence is, and then A is independent of those things. But yeah, that's a critical question to ask always, is where do these constants depend on? So, and this is in fact a universal constant. We'll see. We can see what it is more or less when we do the proof. So if I view this this operation of taking a function, an integrable function, an L1 function, and then associating to it its maximal function, the claim, which I won't do in class today, is that it's not a bounded operator. So we don't have. It turns out it's false. Turns out, rather, let me write this like this. There does not exist a constant C bigger than 0 such that F star L1 for every F in L1. So it's not a, this is not a bounded operator from L1 to L1, but it, however, we do retain, we will prove this estimate. And this is, let me just explain a little bit why this is called, why this object here, and if I put alpha on the other side here, is called the weak, is the sup over all alpha of this object is called the weak L1 norm of F. So on the one hand, so you have what's called Chebyshev's inequality. There are so many different anglicized spellings of Chebyshev. Inequality, which says the following, that for any for every G in L1 of RD, alpha times the measure of the set of all X such that G of X is bigger than alpha, absolute G, sorry, is bigger than alpha, is less than or equal to the L1 norm of G. So this is a weaker quantity than the L1 norm of G. Okay, so how do we prove Chebyshev? So proof of Chebyshev. So proof, just let E alpha equal the set of all X such that it's bigger than alpha. Then integral of G, absolute G, is bigger than or equal to the integral over E alpha of G. And on this set, G is always bigger than alpha. So this is always bigger than or equal to integral alpha. Okay, so that's the proof of Chebyshev's inequality. And that tells you that that if I take, say, sup over all alpha of this quantity, so it's still bounded above by the L1 norm of G. So this the sup over alpha of the measure of the set is called the weak L1 norm of G. All right. So let's now move on to the proof of the theorem. So proof of theorem. Sorry, maybe let me stop and ask if there are any other questions. I see some questions in the chat. Michael, you asked your question out loud, right? And
yeah.
Synchronize the document. Sorry. Okay. Yep. Okay, the document should be synchronizing. Okay, so first, property one. So we're going to try and prove that that the maximal function of f is a measurable function, and this is not so bad. So we want to show f star is measurable. Show this by via showing that the set of X such that f star of X is bigger than alpha is open for every alpha. How do we see this? Well, if X overline is in, let's call this E alpha again, is in E alpha, then there exists a ball B that contains, that contains X overline, and such that 1 over the measure of B integral over B of f of y dy is bigger than alpha, right? Because the maximal function is a sup. So so then therefore there are points if you're close to X bar, then you're also in B, right? Take B to be an open ball, then you can take, if you're close enough to X star, then you're also in B, and therefore you still satisfy this inequality, which means you're still in E alpha. So if X is close enough to X, then X is in B as well, and thus 2. So that's the proof of measurability. Okay. Next, let's show that 3 implies 2. And then we'll just prove 3 directly. So what we're going to try and what is 2? 2 is that that the maximal function is finite almost everywhere. And we claim this follows from this weak estimate in 3. Well, let's note that the set of x such that the maximal function is infinite is contained in the set x for which for every alpha, right? And then, but then this set, the measure by 3, the measure of the set is bounded by a over alpha times the L1 norm. This goes to 0 as alpha tends to infinity, which means that the measure of the set when f star equals infinity is 0. Okay. So now we come to the proof of 3. Now we come to the proof of 3. This requires a lemma, a covering lemma. So the lemma, and these appear all over analysis as well. This is called Vitali's covering lemma. As follows. So suppose B, script B, is a finite union of balls. B1, a finite, this is a finite collection of open balls, let's say. In RD. Then there exists a disjoint. So this is any finite collection of balls. The point is we can replace it by a disjoint collection. Or a subcollection rather. Disjoint subcollection. That almost covers the union. Disjoint subcollection BI1 through BIK of B such that the measure of the union from j equals 1 to n of Bn is less than or equal to, well, 3 to the d times the sums of the measures of the disjoint collection. J equals 1 to k measure of B ij. So even though, so we're going to throw away balls from the collection, from the initial collection we gave. to make the collection disjoint, but we can do this in a way so that we still capture a fixed fraction of the total measure of the set, right? So that this I could put this 1/3 to the d over here, and it means I have the measure of this collection of disjoint balls is bigger than or equal to 1/3 to the d times the measure of the union of the initial collection. So let's prove this lemma. It's not hard. So the observation is that maybe I'll draw this as follows. So if I take any two sets B that overlap, and then so if I take B prime, and the radius of B prime is less than or equal to the radius of B, if I dilate B by 3, so if I make B 3 times as big, this is 3B, then B prime, then B prime is contained in 3 times B. So by 3B, I mean just dilating, expanding the radius to 3 times the radius of B. All right, so this is going to tell us how to refine our collection. So start with B1 through Bn. Pick By1 is ball with largest radius. Then throw out all balls intersecting with Bi1. So just take those, remove all the balls that intersect with it from the collection. Keep this one, and move on. All right. And note that since Bi1 has the largest radius, all of the balls that we removed have radius less than or equal to the radius of Bi1. So that means when I dilate Bi1 by 3, I will cover all of the balls that I threw away, right? So, and note all thrown away balls are covered by 3 times Bi1. All right, and now just do this. Do this inductively, I guess, if you like. If we have Bi1 through now induct, I guess, By1 through Bij, disjoint, then what do? I just take the next ball with lead it with the biggest radius of those that remain, throw away all that intersect with it, and move on. Bij plus 1 remaining radius throw away all balls intersecting with it. So I guess what I mean is that assume I have these disjoint and then nothing else from the collection intersecting this union. And then I'm just left with a smaller collection of balls than I started with that are possibly overlapping. I take the one with the biggest radius amongst those, throw away all that intersect with it, and then move on. And note that I only have to do this at most n times, right? Because I started off with finitely many balls. So I do this finitely many times. Okay, so this is how I end up with a disjoint collection, just throwing away stuff, right? Now the question is now, can I still recover this estimate? And the key point is this observation here. Then the measure of the union from L equals 1 to n, the L is less than or equal to the measure of the union from j equals 1 to k of 3 b I j, right? Where this means I dilate the radius of each of these, which is less than or equal to the sum. Well, these are the sum of the finite subadditivity measure of 3 b ij, and this is just equal to 3 to the d times the sums of the from j equals 1 to k measure of the bij's, right? Because each of these balls is just dilated by 3, and so they cost me this dimensional constant 3 to the d. I think we had one of these. This is one of the homework problems. So this finishes the proof of the lemma. Any question about the covering theorem, the covering lemma? There's an analog of this with an infinite collection, or the countably infinite collection as well.
I'm just curious if this bound is tight.
So what's
it's a very simple argument.
Yeah, what's the best constant you can put here?
Yeah.
Yeah, that's a good question. So I guess 2 times the radius isn't quite enough, right? Yeah, I wonder. I mean, it looks. It looks pretty tight, right? Because you can imagine just like kind of. Okay, so I don't know, but let's just think about it for a second. You can imagine like just lining the so just take the balls of. I mean, so what would tight? I think what would it be is if these bees are roughly all the same size. Right? If all the balls in the collection are the same, maybe we could just prove it like prove it quickly or something. Just if you took all the bees to be exactly the same size somehow, and just like squish right up against each other. So maybe what's that?
Like sort of pack them as densely as you can.
Yeah, packed together. But then squeeze them squeeze them a little bit in so they're actually overlapping a little bit. But we can probably make this overlap as small as we like, kind of, and just proceed like that. So make them overlap smaller and kind of small in a smaller and smaller way. Right. So it looks pretty tight to me. I don't. Does that sound convincing?
Yeah, that makes sense, at least intuitively.
Yeah. Yeah. And so tightly packed ball, a packed collection of balls of equal size, probably that are just barely overlapping, um, probably gives like a saturating example. I think. Yeah, but I'm not. This isn't my um, the type of thing I could answer off the top of my head. Maybe Henry Cohn is the person to ask about this. um, okay, so yeah, and maybe we would need to let the ball. So maybe we'd also let the balls have to get smaller and smaller to like uh, to get a good example, like smaller and smaller balls with smaller and smaller radius somehow. Um, or maybe that doesn't matter. Maybe this is scale invariant. Oh, okay. Yeah, I'm the wrong person to ask. Um, okay, so but let's okay, so we prove this is yeah, like you said, Michael, it's a really simple argument. Um, yeah. Um, and it's but as a deep application, we're basically now the theorem is basically a consequence of it. So so back to the proof of the theorem, proof of 3 from the theorem. So let's let E alpha equal to the set of x such that the maximal function is bigger than alpha. This means for every x in E alpha, there exists a ball Bx, a ball containing x, such that 1 over the measure of Bx integral over Bx of f of y dy is bigger than alpha, right? Because the maximal function is a soup over such integrals. If the maximal function is bigger than alpha, then we can find such a ball for each x. Okay. Now we do something that looks like cheating, but then we're gonna have to be or to make sure that we can undo the cheat at the end, or the boundary proof at the end is independent of the way we cheat. So now so E alpha might be any, we're not sure what the set E alpha looks like, right? And we're in trouble because we have a uncountable number of these balls, right? Possibly bx, right? There might be a lot of x's in here, and so we have a large collection of these balls. So just pick a compact subset of E alpha. Pick any k compact with k inside E alpha. So if I have a large collection and I want to refine it to a finite collection, then I know I can do this if my underlying set is compact. So I'll pick k in E alpha. Compact, k is covered by the union of the bx's, right? Since this covers key alpha, since this collection covers E alpha, it also covers k. K is compact. Since k is compact, can find finitely many x1 through xn such that k is in the union from L equals 1 to n bx L. So you can find finitely many of these balls that still cover K. And now use Vitali. So by Vitali's covering lemma means there exists a subcollection of disjoint balls. I'll call these BI1 through BIK, such that the measure of the union is less than 3 to the d times the sums of the measures of the BIKs. Okay. All right, so these are disjoint. They're disjoint, satisfy, they satisfy I don't want to write this. I want to, they satisfy a ball of B ij for each j is less than or equal to 1 over alpha times the integral over B ij dy. Right, this is by definition. Then we have the measure of k. This means that the measure of k is less than or equal to the measure of the union from j equals 1 to n bxj. Let me call this L. Which is less than or equal to 3 to the d by Vitali times the sum of the measures from j equals 1 to k. Measure b ij. And now I use the estimate above, which is less than or equal to 3 to the d divided by alpha integral over the union. Y, right? Which is less than or equal to 3 to the d over alpha times the L1 norm of f. Okay, so we proved this. This holds, this inequality holds, but it holds for every k inside the alpha. Right, for every k compact. Right, but E alpha is a measurable set. Right, and so this also holds for, and the right-hand side is independent of k, right? Doesn't care about k at all. So we can just take like a supremum over all such k, and we get the measure of E alpha. So so we also have, for Michael's question from before, that the constant a in the proof is just 3 to the d. This is what we set up to prove. Okay, any questions about the proof?
I think I missed the step where you went from the measure of EIJs to the integral over their union.
This step here.
Yeah.
Okay, so how do we know this estimate? Well, how are the balls B selected in the first place? so I'm estimating this by this integral, right? And I claim it follows from each of these this estimate. These are is a disjoint collection, and it follows for each Bij, it follows from this estimate. So where did this estimate come from? Well, this is how we picked these balls in the first place. I just rewrote this estimate.
Oh, right, because X is in EA.
Yeah, exactly.
Okay.
X is an EA, so that means I can find such a ball. And then the collection I built at the beginning is just the union of all these balls. And then all I did was refine the collection. So I threw out a lot of them, and I was left finally with many of them. That still covered most of the set that are disjoint. Might not cover sorry, they're disjoint. They still cover K. Sorry. I have a non-disjoint set, the collection that covers K. I can refine it to a disjoint collection that may no longer cover K anymore, but I only I cover at least a fraction of the measure of K, and that's enough for the direction of bound I want to prove.
I have a quick question as well.
Yeah.
So it's clearly necessary that our original function f is an L1. Otherwise, you might have the maximal function is like infinite everywhere. But
Yep.
where in this proof of part 3 did we actually use the fact that f is integrable? Like which bound is that in?
I see. Okay. So we didn't really use that f is an L1 function. We rather only used that f given a point x, that f is integrable near x. Right? Okay, so on the one hand, we needed to make sense of like for measurability of E and all of these sets, we need to make sense of the integral of f sometimes, right? But we never, like you say, we never really considered the full like L1 norm of f. And let me say a bit more about that in a minute. But yeah, your instinct is right. We didn't really make use of that fact. Or we do here because yes, I mean, okay. So let me just back off a second. So for this theorem, it's kind of vacuous. This theorem about the maximal function is kind of vacuous if f is not L1, because on the right hand side we just have infinity, right? So nothing really makes sense for 3. Like this estimate isn't an estimate, right? If f is not an L1, right? It's just this is just saying that some set is less than or equal to infinity. The measure of some set is less than or equal to infinity. Sure. So it is important. Like it is important here, and then viewing viewing the maximal function as the question about whether it's a bounded operator from L1 to L1. So that the context is like the questions that we're asking don't make sense out of that context. What am I saying about if we go back to this initial question that we're studying, right? If about picking a point X and then studying the this object just at the point X, then we're not making use of the like full integral of f. We're always just fixing a ball and integrating f times the characteristic function of that ball. So to get back to our initial problem that we were thinking about, we're not really considering the full integral of f, only rather the integral of f around balls that contain a point x. So that's what this is what's called the local L1 norm of f. So we'll get to that in a second. But you're right that we're only really seeing the local L1 norm of F come up in the question that we set out to study.
Can I ask 2 more questions?
Yes, and my last comment is this. Sorry, yes, I'll get to you. Last comment about the previous question is does the maximal function? I think you actually said this in your question, right? The maximal function, if f is an integrable, then the maximal function is just identically equal to infinity, right?
Yeah, I think also in particular that was criteria 2 that was confusing me, and then the proof that 3 implies 2 actually breaks down if f is not integrable, because we use that like a over alpha times the L1 norm of f goes to 0 as alpha goes to
infinity. So
yeah.
None of this stuff about the maximal function makes sense for unless we start off with a L1 function.
Yeah, it makes sense.
If f is an L1, then the maximal. Well, okay, we could just say we can have a not so interesting statement. If f is not an L1, then the maximal function is identically equal to infinity. Okay, Samuel, your questions.
A very quick question first. To finish off with the last part of the statement, the proof, do we just take supremum over all compact sets?
Yes. Yeah.
Okay.
Take sup over all compact sets, and remember that we can obtain for a measurable set we can obtain the like remember exterior measure. We can attain the measure of E alpha that way for a measurable set. Take sup over all compact sets contained in E alpha.
And you have talked about f star finite almost surely, but not necessarily L1.
Yeah.
So is it essentially bounded?
What does essentially bounded mean? What do you mean by that?
Bounded almost surely. So I mean,
I see.
Number,
I see. Bound. I can find a uniform bound outside of a set of measure 0. No, I don't think so. I don't think so. I don't think so. Let me wait. Actually, let me think about this. Maybe it is. Maybe it is. I don't know if I could do the proof in a reasonable amount of time, but I think you should think of this as sort of just barely missing to be an L1. If you still have this weak L1 bound, you have very good control. You see over the sets where F star is big. Like just pick an alpha, right? Pick an alpha very big. This is some number, right? Then this set becomes very small, right? The set where F can be bigger than alpha. So suppose it's not bounded. Not essentially bounded. Then I could find. Yeah, let me. I'm trying to see if I can prove it in my head, but I don't know if I'll be fast enough to do it in a reasonable amount of time. I would try to. So if you want to try to investigate that question, I would try arguing by contradiction, and then seeing if you could using this as a tool. That would be my try at a proof, but I'm not sure if it's right, if it's correct or not.
I mean, if it is right, then I wonder if the linear, even though the linear operate, sorry, even though the operator M is not bounded in L1, but if we know that F star is in the space of all essentially bounded function, then can we say that M is bounded with respect to
To L
the
infinity.
norm of that space?
I see. Do we go? Does it go from? Does this go from? Is this a operator from L1 to L infinity?
Yeah.
Oh boy, I would be failing my graduate school topic oral exam right now with these. Let's see. So, yeah, I sorry, I'm not able to do this in my head.
I think if we use something like 1 over x to the power of something, that may fail.
Yeah, yeah. So the examples, you could, so we can, so a good exercise I think that'll help you answer the question is try to prove that it's not bounded from L1 to L1 by finding a counterexample. And I think this should also give you the I think this will also give you the counterexample to the claim that you suggested as well. Yeah, if I remember correctly, yeah, you were gonna want to make no. Yeah, I think we can make the maximal function and kind of um, be not integrable. So there's two ways we could try and make it be not integrable. And I was getting hung up on the first way. One is by like you say, like making its tails decay too much as we go to infinity, decay slowly as we go to infinity. The other is by making it grow too fast around a point. And I think we can achieve the latter. Probably, but we could probably achieve both. But I think we can in particular achieve the latter. The latter, which would violate the essential boundedness criteria as well. Yeah, right. Because yeah, okay. I think the first thing that you said is probably false. So yes, it's probably false. But thank you for the good questions. I'll try to find some time to think them through and explain them next time a little bit better. Okay. I see now that my PhD has been rescinded, as I'm hearing over the wires. So I'll no longer be teaching the class to you guys. Oh, sorry. No, just kidding. My PhD would be rescinded every day if it was about getting stumped on questions like this. The next thing that I want to prove is the Lebesgue differentiation theorem. but maybe I'll state it and then start the proof next time. So the theorem, and this is an answer to our question that we started off with. This is called the Lebesgue differentiation theorem. Theorem, which says that if f is in L1 of Rd, then the limit as the measure of the ball tends to 0, where we take this limit over all balls that contain x of 1 over the measure of the ball integral over the ball f of y dy is equal to f of x for almost every x. Okay, so this is the theorem we're after. This is true almost everywhere. It tells you that the fundamental theorem of calculus holds almost everywhere, holds for almost every x, as long as f is an iterable function. And we'll prove it next time as a consequence of the two deep things that we've proved. One is the maximal function estimate, and then the second is the density of continuous functions in L1. So with compact support. So we'll just approximate f by continuous function compact support, and then the errors that we'll make will control with the maximal function estimate, and that's basically it. Okay, but we'll do that next time carefully. Restate this and do this next time carefully. Any other questions before I wrap up? Let me sync the file. Okay, guys. So I'll see you all on Thursday, and I'll give some homework this week again. So I'll assign homework on Thursday to be due next Friday. Thanks, guys.
Thank you.
Yeah, can you synchronize?
Yes, I think I just did. It should be uploading.
Okay, thank you very much.
Thanks.